Hey everybody, how you going? Just gonna get started in a minute. How come I seem really oversaturated? Maybe I should always stand over here when I'm lecturing, so it's not too much crazy light. Turn that one down a bit. Whoop. Maybe turn this one. No, that's not right. Okay, yeah. I like to get the cameras exactly right, exactly right in my streams, but it keeps changing its exposure depending on what the screen looks like, which is a bit frustrating. Okay, I'm definitely streaming, I'm definitely recording. That's great, I can hide that guy. Ubuntu probably it's got a blinky little system update thing today, so it might be saying, why don't you upgrade to 2004 or something? Which I probably won't do while I'm in the middle of giving you guys a lecture. Welcome back to our Friday lecture. It's wonderful to be here again to talk to you. The topic of today's lecture is concurrency and synchronization or asynchronism, sort of two kind of terms. Basically, when things on your computer are happening at unpredictable times, what can happen and what can we do about it? Now, before we get straight into the content for today, I want to just have a little bit of a chat about the mid-semester exam. I just want to give a shout out to a few tutors who were involved in marking the exam. I don't think it would be fair to name them in particular, but there are a couple of tutors who have just gone above and beyond to get these grades back to you. And the reason that we did that is because we really wanted you to have some confidence coming up to census date that you were tracking well in this course and get you some good feedback about your understandings of everything so far. So the big news is that now we've looked at the mid-semester exam, I'm really happy that we are able to do, I suppose, exams that have academic integrity in this online format. I'm really proud of all of you students for taking this seriously and coming together to treat this like what it is, which is a way for you to check your own knowledge and a challenge for you to tell me what you understand and explain to me the concepts which we're learning in this course. So really, really big well done. I'm just going to go to the page where we have the statistics for the grades for this exam. Now, the average grade, the mean for this mid-semester exam was 59. And this is actually only counting students who attempted the exam. So there are a few students who did not attempt the mid-semester exam and they obviously didn't get any marks. They're not included in this analysis. We've got a distribution over the 60 marks of the exam, which is sort of roughly normal-ish. I mean, I'm not going for a normal distribution in any of our assessments, but it turns out that when you give 359 people the same exam, there's a great many of you who have an understanding of the topic somewhere in the middle, and then there's a few who are have really amazing understandings of the topics, and then there's a few who need to keep working on their understanding. So we end up with a kind of normal population. The mean was 59, as I said. I think more interesting is the median, which was 61.25. So that's the sort of the middle point in this population of students. And I think that that's acceptable. It's very similar to last year's mid-semester. So what we can conclude from this, or what I can conclude, is that the mid-semester exam is still serving as an excellent tool for analyzing what you know and what you don't. It's great that you get some really good feedback in the online format. You can now look through your whole exam paper. I've written out sample answers for best case scenario grade answers. Not everyone will write as much as I wrote in the sort of sample feedback answers, but if you want to know what I'm looking for, that's an example of something which really ticks all the boxes. You get to see all of the places that you missed out on marks in the multiple choice. And of course, you're certainly free to come and complain about it in Piazza, although we have worked incredibly hard and incredibly carefully on this exam, and we don't always agree with students that they should just be getting some more marks. So you have to accept sometimes that if you haven't demonstrated your knowledge in a way that's clear to us, even if you know more than you wrote down in the exam, if I can't tell what you knew through the solution that you provided, then I can't give you marks for it. So the distribution shows that a large number of students the majority of students are doing fine in this course. You're passing the exams, you're in the sort of credit D and HD range. It's really, really wonderful to see, and I'm particularly pleased to see a bunch of students who were getting almost full marks on this exam, which is wonderful. I'm also really proud of a bunch of students who are in this bunch around 35 to 40. I think that there's students there who maybe are putting in a lot of effort to get on top of this material. They're working really hard to make sure that they're keeping up with online education. And I just want to say that if you're in that situation, I'm really proud of you. I think you're doing great. Keep it up, keep coming to labs, keep engaged, and you're going to be fine in this course. Where I'm concerned is that there are some students who are really not up to scratch with their knowledge yet. Right down the lower tail of this distribution. I suppose I'm too big to see it right now, but I'm concerned that if you're down in the lower end of the distribution, you're nowhere close to passing this exam, then it's getting to be quite difficult for you to catch up. And given that it's now census status today, I hope that there's people there having a think about whether continuing with this course is a good idea for them. I'm certainly not interested in kicking anyone out of the course. We're here to help everyone improve, and I certainly think that there's students who are kind of around the pass level or just below the pass level, didn't quite get up to that level, who with engagement and working with us can certainly improve their knowledge and their approach to exams as well. Taking exams is certainly a skill. And I've read a lot of exam questions at universities now, or exam answers, and I know that there's some people who have really great systematic ways of answering questions, making sure they mark off everything that the examiner has asked them to do, answer all parts of the question. And there's some people who maybe just answer the last part of the question or get a bit confused about which parts of the question they're supposed to answer. So that's a bit of a digression, but there's certainly scope for every student in the course to improve, to get up to standard. But I know that some people are really struggling, so I hope that they have a think given the feedback coming through today. Okay, now, yeah, my upper half is approximately normally distributed. I'm a bit of a normal distribution as well. Thanks in the chat for that. Now the assignment 2, of course, is going to be due very soon. I hope that, just going to the assignment for a second. It's due next Friday. I really expect that everyone has started on the assignment. I know from looking at the Piazza that there's lots of students trying things out, having great discussions, asking us questions. And sometimes when we get questions from a few students, we just sort of distill the information from that into a note, which we put back to everybody, so that there's a great kind of feedback loop between people asking us questions, even if they're private. So really pleased to see everyone's efforts happening in assignment 2. Okay, I'm going to jump into the topic now, because I think we have a lot of logistical information in this course. We don't always need to go through it in that much detail. Today's topic is kind of part 2 of what we started on Tuesday. This is about asynchronism. So where were we in the course so far? Well, I'm just going to check that I look correct in the... Yeah, that looks okay. I've kind of got my head in the way of in the way of this stack on the right-hand side. Where were we? Last time we learned that there's this thing called an interrupt, which can happen on our disco boards. And an interrupt is a way of something external to the CPU or internal to the CPU, some other piece of hardware, to send a signal to the CPU and say, you need to stop what you're doing right now and look at something else. And we learned that this interrupt is a sort of hardware intervention within our CPU. It sort of hooks into the sequencer, stops the sequence of operations, and deliberately moves the program counter into a different bit of code, which is specifically designed to handle the interrupt. Because it's handling the interrupt, we call it a handler, which is great. We know that the interrupt system has these features built into the hardware which will automatically save everything we were doing in our code, the program counter, where we were up to in our code, whatever flags we had set, they'll get saved, whatever registers we were using, the caller save registers will be saved here. And then the handler has some responsibilities as well to save the callee save registers and then do its work. Then when the handler returns, it returns to this special link register value, which tells the CPU, okay, you're returning from an interrupt now, you need to put all of this stuff which you stored on the stack back into place so that the program can continue from where it left off. And the really important thing to note is that an interrupt can stop our program at any time, And of course, there are some ways to prevent some interrupts from happening, and there are some kinds of interrupts which can't be prevented, or they're at such a high priority that they are allowed to get through, like the reset button that always stops the CPU. Now, what I want you to start to think is that the interrupt system is able to save all the bits of our program, put it on the stack or sort of keep it somewhere safe, so that then it can put the program back just the way it was before. And I think it's useful to start thinking at this stage, like how long it might be before your program gets back to being active. Does it have to be a short time? I think I said last lecture that it ought to be a short time. We like it to be short so that our program can get on with its work. Otherwise, we'd be prevented from doing anything. But if it was a really long time, is our program even going to notice? Is it like if you put Han Solo into carbonite, put our program on ice, and then thaw it out? The program comes back to life. Has it even noticed that it was sleeping? Not really, right? Because all of its important information, all of its context, has been saved onto the stack, and then the handler loads it all back in. The program doesn't even know it was gone until maybe next time it checks the time. Wow, it's hours since I left. How'd that happen? So this leads us to the topic of today. I just want to go back to analogy time for a minute. Remember on Tuesday, another important topic of the conversation last Tuesday was on the analogy, considering the analogy of your disco board being a starship, right? And then there was the captain, right? Captain Picard was the captain of the starship. And Captain Picard gets interrupted by Commander Riker, right, with some important information. Captain, look! And now Captain Picard has, in some sense, stopped being the captain, right? The Commander Riker is now the captain. He's the handler of this interrupt. And in fact, Jean-Luc Picard has taken his leave of the captain's seat and importantly moved over here. Okay, you with me so far? Now, what if the next thing that happens is instead of Captain Picard going back into the captain's seat and being in command again, then Geordie LaForge sits in the captain's seat instead. Geordie's obviously not the captain, but it's kind of like, well, whoever is sitting in the captain's seat maybe is the captain. So I guess what I'm suggesting to you in a bit of a roundabout way, is that maybe we could actually run 2 programs on our disco board. We could actually run 2 programs. I'll just give you a second to think about the implications of that. There's a bit of chatter in the chat, chatter, of what might happen if the stack is full and there's an interrupt. Well, Mitch has correctly said that a stack overflow, that is where our stack gets too far and can't go any further, would be bad. Either the stack is going to overwrite some memory, or our disco board's going to try to store to memory which is not available, like it's storing to memory addresses that aren't writable. And if that's the case, then the disco board will crash because it's an illegal operation. So you'll end up with another interrupt, the crashing interrupt. And certainly in the way we're setting up our disco boards right now, there's no way to prevent that if it happened. We just sort of, it's unlikely in the kinds of programs we're writing right now. So back to the topic, you've had a minute to think about what might need to happen to switch on your disco board to a different program. Switch in your disco board to a different program. So the big idea here is, can you have 2 or more main programs and use interrupts to switch between them, like as some kind of trick to get the interrupt to, instead of putting your program, the first program back, it actually loads a second program. So this is called context switching. This is just a short topic. And the question I've got for you is, what is a context? Well, a context is the set of information that needs to be saved in order to save a whole program and put it right back the way it was before you stopped it. The set of information that needs to be saved for a program to start up again after an interruption. And in fact, our interrupt already saves all that, right? It saves the whole context. It saves the program counter location where we were up to in our program, in the code. It saved all the flags that were important to our context. It's saved all of the caller save registers, and then the handler has the responsibility of saving the callee save registers. So our context has already been saved, which is super great. And how are we going to switch now to another program? It's actually not that complicated now that we've got this information. So we need a few more things. We're going to start over here. This program's running. I suppose I could have had a little green light or something to indicate that it's running. This guy's going, running. And we've got a little bit of extra storage space somewhere. I don't know where this variable is stored. It's not going to be on the stack. It'll be in some other allocated memory, statically allocated memory or dynamically allocated memory. Somewhere else, we're storing some information. And what I'm going to call this part, this is our first program, program 1. I'm going to call that process 1. And I'm going to call this other program process 2. So process 1 has got its code, that's important, tick. It's got its stack, it's important, tick. And the program counter is in that code, it's running away, running like clockwork. Load and store is going, we're twiddling some values, doing work we need to do. The stack is existing and the stack pointer is moving up and down. We've got some context, some stack frames here from different functions. And then we've got this extra bit of information that we're going to store, which this one, PID, well, that's going to stand for process ID, so that should probably be process 1 in there somewhere. And then PCB is going to stand for process control block, and that will just be a little bit of memory where we're storing some information about our process, this one sub-program. Now, here's our handler, our interrupt handler, and in fact, I'm going to change its name from being just handler to a dispatcher, because its job is going to be to say which program is in charge at any one time. And at the moment, this one on the left is in charge. On the right, we've got a different bit of code somewhere else in memory, we don't know where, and then actually a different stack, even though it looks similar, it's got the same frame stuff, but this might be base 2, and that's base 1, so they're somewhere else in memory. Base 1 is at some place, and base 2 is another place. And we can just assume that they're both pretty big, they've got enough space. So now the goal for this context switch is to stop this one, that one's not running, and start this one up. So here's what happens. An interrupt occurs. So we move our control into the dispatcher, the interrupt handler, and all the same things that we expected to happen from last week happen from Tuesday happen with respect to this interrupt. Our program counter is saved, our flags are saved, our registers are saved, and then the dispatcher does a bit of work, saves the callee saved registers and local variables, and puts them on the stack. Okay, and now control program counter is pointing into the dispatcher. And our stack pointer is still here. Now, right now, if we BXLR'd back from the dispatcher, or put the callee save registers back and BXLR'd into from an interrupt handler, our control would go right back into this process. Right back into that one. And what we want to do is to put control back into this one. And there's actually it's not very hard in this model. This is granted a perhaps simplistic model of how we do this, but it's not very hard to trick our CPU into starting process number 2 instead of process number 1. Can you see what it is that we have to do? One little thing we've got to do. So it's over here, right? If we BXLR, the CPU is going to look in the stack, look at the address that the stack pointer is pointing to, and assume that it's going to find there all of this stuff that it needs to put back. Registers, flags, and program counter. And if our stack pointer actually points over here, then we can get these ones back instead and start up this program. So this one's got the PC pointing to this code. This one's got a program counter which is going to point into that code. So this is where we get to my step 3 of this process. Yeah, someone's chucked in the chat changing the PC to point to the second stack location. Well, this stack location has its PC already pointing to that code. So we don't need to change the PC. The PC's value is going to get put back by the CPU. All we have to do is make sure that the CPU is looking in the correct stack to kind of get these values back. So here's step 3, swapping to the new context. So we take this stack pointer from, we take the stack pointer from process 1 and we're going to store it in memory in our process control block for process 1. There's probably a whole bunch of other stuff we need to put in the process control block to get this to work correctly, but this can just be a toy model for the moment. So this SP is now stored there, and then our dispatcher is going to take the stack pointer from process control block number 2 and put that in our stack pointer register, R13. Okay, so when it does that, now we're ready to BXLR out of the dispatcher. I mean, we'll probably have to manually put back these caller save and local variables, but that's easy, just popping those off the new stack, which we're looking at. And then we BXLR out of the dispatcher. The registers, they R0 to R4, go back where they need to be. The flags go into the program status register, and PC goes to R15. And then our program starts up again. So we get to step 4, returning from dispatcher, the stack pointer is now pointing into the new stack at the base of it, sorry, at the top of the stack, and the program counter is pointing into our second program, and our second program is ticking along. So now we can actually switch from one program to another program. And you might think that this seems like a little bit confusing and convoluting, but I'm sorry to break it to you that unfortunately your computer is doing that all the time. If you've got multiple programs running, all of your computers are running multitasking operating systems, and they're all quite happy to run multiple programs and just to keep switching between them. And they're switching between them at a rate that you don't even really notice. And there's not a thing you can do about it. It happens all the time. So I guess within this dispatcher, we're going to have some kind of algorithm for making sure that each program that we want to run is getting enough time to get stuff done. That would be a scheduling problem. And we'll talk a little bit more about that when we talk about operating systems in a few weeks. But right now we've now made this link between a very basic thing in our CPU of changing between, of interrupting the CPU and doing something outside of your program context, and now switching to a completely different program, multitasking. By the way, like normal computers that people had weren't always really multitasking. Like back in the DOS days, MS-DOS, those computers, that operating system was really only single tasking. It was not attempting to give different processors equal goes. But now all of our modern operating systems do this as part of its organization. Someone's just asked the question, is this switching done at the hardware level? No, it is not. The switching is done at the software level, but it uses the hardware facility for interrupts in order to do that. And in fact, that hardware facility for interrupts is crucial. If you don't have interrupts that can stop your program from continuing, stop any program from continuing, back to a handler to do something else, then this situation doesn't work. So it's reliant on hardware features. Yeah, I'm just going to let there be a few seconds silence. We'll see if there's any further questions about that. Any other questions? I should have my my music come back, some question music, but I didn't organize it for this week. It's been a very busy week organizing the mid-semester exam for everybody, and these lectures and a few other tasks as well. Okay, not seeing any more questions right now, but if you have one, just pop it in the chat on Teams and I'll get to it. I don't really look at the restream chat. Ooh, someone just asked if I could explain the last step. So the crucial bit was that once if the stack pointer from this other program control block is put into the stack pointer register R13, then when we return from our interrupt handler, then our program context from the second process is put back on the CPU instead of the program context from the first process. So the first process and the second process have independent stacks. This one starts at one place in memory and this other one starts somewhere else. They've also got an independent program counter. So they each know, this one knows where it's up to here and this one thinks it's up to here. They've each got different flags, different registers. So if we have to do it carefully, mind you, all we have to do is arrange it so that this stack pointer points to the second stack. Then when we return from the interrupt handler, all the stuff that the interrupt handler has to deal with and all the interrupt returning stuff on the CPU, remember the special link register value that we talked about on Tuesday, all of that will get put back onto the CPU instead, and the CPU will start running the second process. So now the CPU is running the second process. Program counter is pointing into the second process's code. The stack pointer on the CPU is pointing into the second processor's stack. And the first process, it's all saved. That one's been put on ice, put into carbonite. So it's saved until the dispatcher switches back to it later. So the big picture thing is to consider whether any of these programs is going to notice that it's been switched out when you switch back. So I guess my Star Wars analogy was a bit flawed, because when Han Solo is thawed out of carbonite, he is a very sick guy and he's not very happy that he's been stored in carbonite. I don't really understand the whole carbonite concept anyway. What are they storing in this carbonite? Why are they... Do they often store people there? Oh, there's a really hard question from someone in the chat about interleaved multi-threading utilizing PID metadata. We're going to talk a bit more about more complicated versions of this at the moment. At the moment we have one processor, we have no operating system. This is just the basic concept of a context switch. We've got in a few weeks time, we start to put a few more building blocks into place in this course. And then someone else asked, this is technically not real multitasking, isn't it? Why? I think it's multitasking. You got one program doing something, that program might get, 100 milliseconds to do a bit of stuff, and then our CPU switches over to the second program, that gets 100 milliseconds to do some stuff. We don't have like any command interface or a user interface to this computer at the moment. We're just running two programs, two tasks, therefore multitasking. I don't see why it's not multitasking. Of course, it's a simple model. There's probably some other stuff that we might need to save if we were going to have so-called processors, but yeah, we're just thinking about it at a simple level for today. I'm going to move on. Actually, these programs are not going to notice if they've been switched out and back. How would they know? They would have to potentially check a timer or check the time if they've been keeping track of the time somehow, and go back and find out oh, wait a minute, the time is different than the last time I checked. That means I must have been switched out by somebody. And even if they can't notice, we should worry about whether anything can go wrong here. And I haven't heard anyone saying, I don't think it could go wrong. And someone in the chat has just asked, could you use this to create a harmony? I'm going to say, I think this would be a bad strategy for creating a harmony. Don't do that, no. Because you would sort of be playing a little bit of one note for amount of time and then a little bit of another note for an amount of time. Whereas to do harmony, you have to be doing both at the same time. Otherwise, it's not going to sound like harmony, not going to sound like two notes. We're not going to talk about digital synthesis this lecture very much, so I might move on from that question. So the big picture thing here is things could go wrong if both programs here are sharing data. So if one program is looking at some data, maybe it's set a variable to be 10, then the second program wants to set that to be 11. We go back to the first variable, and it might find that the number it had put in there has changed in between. Yeah, I think there was a really great suggestion from someone who said, well, this might be one of the reasons we want to not save the program counter in the register in the link register during an interrupt procedure. We save it on the stack, and then we go and do our other work. And that's absolutely true. But the tutor Mitchell has just jumped in and said, well, we also want the CPU to be able to do this task for us of putting back the call or save registers, and it wouldn't know to do that unless we had the special link register value in there. So now we get to the main topic, concurrency and synchronization. So we've now got this prospect that perhaps two programs could be running, and they're not exactly running at the same time. It's like we do a little bit of one, and then a little bit of the other, and then a little bit more of one, a bit more of the other, a bit more of the one. So it's sort of switching back, But from the program's point of view, they're running at the same time. The program never notices that it's being stopped. All it can see is that it's moving along through its thing, and if it looks over another process, it sees that that guy's also moving along. And they may be moving in different ways or different speeds, but they're both moving from over time. And then synchronization is our problem of dealing with how to organize our access to shared resources, things like memory which are shared. So we're going to see an example now. This is our first of our many little examples, little brain teasers this lecture. We've got 3 programs, and these are just simple little programs written in a high-level language. Simple little programs, but they're all accessing one value called G. So the question is, what's the value of G at the end of this program? Given that these programs are potentially stopping and switching, stopping at any time and switching to another one, and we don't know which one's going to be first. Now, I'm going to give you a second to think about this, but I guess there could be potentially many values of G, and my question is, which one might be the smallest and what might be the largest? So have a bit of a think about that. Hopefully I hear from a few people who aren't just the usual suspects, even though I do have some good chat from them in the Teams chat. I'm giving you a few minutes to think, so I hope I see some more messages. Just have a look in the restream chat. Oh, someone's jumped in. Thank you, Oscar. Thought was that the largest G might be 24. So our way to get 24 would be that we run this line first, set G to 1. So we're looking in memory and setting it to 1. We look at this line second, and then we look at this line third, and that would be set G to 3. And now we do this one where we load G, load G, load G, and add it together. So now G is 6. And then we've got this one where we add 2 G's together, and we've got 12, and then we do this one, we get 24. Someone else, thanks Isabel, suggesting 2, which is excellent, an excellent suggestion. So how could it be 2? Well, first of all, we perhaps deal with this thread. That one runs first. G equals 2, G equals G plus G, so G's 4. Now we overwrite 4 with 3, and then we overwrite 3 with 6. And then we go back to here, and we do G equals 1, and then G equals 1 plus 1 equals 2. Now I'm potentially going to complicate things for you in a second now, because if we think about how this might be arranged in assembly programming, which of course it will be eventually, all your high-level programs have to get compiled into something to run on the CPU. And instead of just 2 lines in each one, we've now got like 7. So this is the same program, right? Over here we're loading an address, G, for that label into R4. Now we're going to put 1 into R1. We're going to store R1 into R4. So now 4 is in that word. That's G equals 4. That's done. Then we load back the address of G again, or we load it again. We loaded it before, but we don't know that. We're just going to do it again. Unoptimized assembly code. Then we're going to load up whatever was in that value. This is g equals g plus g. Figure out what g was from that address in memory. Load it in, put it in R2. Now we're going to double it, add R2, 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 and then we're going to put it back. And in fact, now before, in the previous slide, we only really had three places to interleave, right? Or for our 3 processes to get interleaved. Uh-oh. It could be stopped and started there, stopped and started there, stopped and started there. And now we've got way more, right? It could be stopped and started there, 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 there. Ho-ho! And Adam Rowland has just suggested, thank you, Adam, race conditions, putting this this concept into our brains. So, you know, just sort of briefly, the idea of a race condition is that there's 2 programs and they're trying to access some shared resource, and you know, they can see this goal in the distance, they're racing towards it, and they don't know which one is coming first in this little race. So our outcome of the program is kind of impossible to predict because we're not sure of which one of these processes is in front and which one has done the load, done the second load, done the doubling, right? So this is going to get messy. In fact, I don't want to try even to analyze this. It would be a crazy idea to try to pull this apart and work out all of the little connections that could possibly happen. So let's move on, right? Move on and just admit that we have a huge problem. If we are sharing memory, we don't have any way of controlling it. So maybe just for a thought experiment, we can start to think in terms of an analogy. This one's not a Star Trek analogy, it's an everyday analogy, and it's called the too much milk problem. So here's the too much milk problem. I'm going to make myself big so I can tell you a story about the too much milk problem. There's 2 roommates in a house, okay? And there's 1 fridge. Normal houses have 1 fridge. Perhaps if you're like having some kind of war of attrition with your roommates, you'll have 2 fridges, but this is a normal household. When housemate number 1 comes home after work, assuming we all go to work, they open the fridge door, they look inside and they say, oh, there's no milk. So they close the fridge door, walk out the door and go to the shop to get milk. Okay. Meanwhile, they're at the shop. Meanwhile, housemate 2 comes in, they open the fridge door and they say, there's no milk. They close the fridge door, walk out the door of the shop to get milk. Roommate 1, meanwhile, comes back, opens the fridge door, puts their milk in, closes the door, goes away to do something else. Housemate 2 comes home, opens the door, they're holding milk, there's milk in the fridge, there's too much milk, okay? This is exactly the same problem as we've had before. There's 1 shared resource, there's 2 processes accessing it, and we're not sure in what order they're going to look in the shared resource, open the fridge door and have a look, and how they're going to, what they'll find there when they do. So there's a little bit of an explanation here for people who are maybe downloading the notes later. But my question is, what is the solution to this? So, you know, there's got to be some way to prevent this happening. And in a real housemate situation, if you've got a share house, we do have solutions for this. Yeah, so that's right. So someone's just jumped into the chat. Thank you, Joseph. Great idea. We're going to put a sticky note in the fridge, on the fridge door. When they open it up in the milk spot, the sticky note will say, I've gone to get milk. And so when person 2 comes home and opens the fridge door, they're like, that's fine, I don't need to get milk. Perhaps we could also have a lock on the fridge door. So whenever someone goes to the shops, they first of all open the fridge door to check all the things that they need. Close the fridge door, lock the fridge door, go to the shops. Roommate 2 comes home, they can't open the fridge to even see the milk. This is a bit of a sadistic solution. And Then person one comes home, they've got the key to the lock, they open the lock, open the fridge, put all the stuff they need to see it, and housemate two, now the housemate two can open the fridge, see, oh, well, you've got milk, but I needed mustard. Now I have to go back to the shop. So they might have to wait there. And potentially we have a situation where if one housemate locks the fridge, goes to the shop, while they're at the shop they get distracted, you know, go visit their partner somewhere else across town. Person two comes home, they need to make dinner, and the fridge is locked. So there's a potential sticky situation in brewing. It's potentially a sticky situation brewing. So what we need in our assembly programming is some way to lock the fridge. We need something like a note or a lock or some mechanism outside of our normal loads and store accesses in order to do this. And there's actually no way to solve this with what you've got, the tools you have at the moment. There's no way for one process to ever know that some other process has been accessing shared resources while they were away, accessing memory. So far we don't have a solution, but I'm about to explain what the solution might be. Bear with me, we've got another little code one to look at and I want to just bring this in because or a few more bits of theory and then another bit of code. I'm going to talk about what we need to happen here, which is that in our programs there might be some kind of section of the program where our program is accessing a shared resource. And from now on in this lecture, we're going to call that a critical section. Important bit of the program where they're accessing the fridge, accessing the memory, accessing some peripheral that's shared. And we need some way to ensure that only one process at a time can enter critical sections. And when we're doing this in computing, this is called mutual exclusion. The principle of mutual exclusion is that in a critical section, only one process can enter at a time. And when the second process can't enter until the first process is finished. Mutual exclusion. And sometimes in computing also we say a mutual exclusion. We even call it mutex for short, M-U-T-E-X, a mutex. And that means it's some kind of solution or scheme that we have for solving this problem. So a mutex is a program construct which allows us to implement mutual exclusions. So without one, let's look at a slightly more complicated program, a for loop. We've got one shared variable, count, and this for loop is going to count up, add 1 to count each time, count from 0 to 100. And the second for loop is going to count down in minus numbers. So if this one was just running by itself, that would go to 100. If this one was going by itself, it would go to negative 100. And if they are running sort of interleaved, as we know, anything could happen, right? We're not quite sure. We're not quite sure at all what the outcome could be. When we look at it in assembly, we can see that within each of these for loops, going back to our control flow lecture if you want to remember how to do a for loop neatly in assembly, but here's a very neat for loop. We start with our loading up the address of our variable in memory, count. We have a counter variable, we're going to store that in a register, R1. Inside of our for loop, we've got a label for the start, we compare R1 to 100. If it's greater than 100, we exit the for loop, and if it's not, we load our value of count, add 1 to it, store it back into memory, and then we increment our counter variable into R1. Now, second loop has R1, R2, R1, R4 as well, but of course these are different programs, so it's a different R4, right? This R4 is stored to the stack when this program on the left is switched out, and then the R4 from the other program is put back into the CPU. So even though we've got two R1s here, they're not the same R1, they're different. It may as well be running on different CPUs. They could be 2 CPUs in one computer, multi-core processor, running 2 of these programs, and they're both accessing the same memory. So this bit here is the critical section This is the bit we want to protect because this is the bit where we're accessing the shared resource. And we could get these weird things that happen, like if each of these programs was going one line to one line to one line to one line to one line, one would sort of count up and one would sort of count down. And then the answer might be 0. Or we could have it that this one on the left loads up the first R2, or it gets to here before it's even loaded any of the program, or gets to here. The whole of the second one runs, and then this one just overwrites it. So we may not even notice that the second one ran at all. It may make no difference. Someone's suggesting we're cooking now with CPU components, cores and threading and scheduling, queues. Yeah, we have to wait for our architecture and OS lectures a little bit later to talk about that stuff. So this is what might happen in assembly. We're staying in assembly now. And how do we solve this? Well, here are the tools that the ARM processor gives us to solve it. This is a big one. This is our solution that we have on the Disco board. There's 2 more instructions that you get to see. And the first one is a special kind of load with EX, and the EX stands for exclusive. Second one, different kind of store with EX for exclusive. By the way, it's really beautifully laid out in these slides. These are thanks to Uwe Zimmer, who often teaches in this course. He creates really beautiful slides doing these concurrency topics. He's also a lecturer for concurrency and distributed systems in semester 2. So many of you will be seeing a lot more of his slides sometime soon. And I've borrowed the slides just to look at these topics. So how does literx and strx work? Well, the exclusive load is going to load R4 into R2, and meanwhile, at the same time as it does that, it's going to have a little storage place and put this address into that storage place and say, I want to tag this one as exclusive. I'm using that one. Tag R4 is exclusive. It's got a little box just for that address, the exclusive store. And then we do our work. And then the strx command, which is actually, the syntax is not quite right here, but we'll just assume it's right. The strx command, it stores the value of R2 into R4, but before it does that, it checks that little box. And if that little box still has R4 in it, we've still tagged R4 as being exclusive, then it lets us do the store, lets us put R2 into R4, into that count word in memory, and then it returns a number which is 1, which means that it worked. I think it's 1. Compare non-zero. No, it's 0 if it worked, yeah, just like processors. So it returns 0 if it's worked. And if it didn't work, if it looks in the box and it sees, uh-oh, it doesn't have that address in it anymore, it's got someone else's address, or it's got nothing in it, then we know that someone else has been messing with our memory, and the strx doesn't let us do the store. And in fact, in that case, it returns a 1 to us. And then all we have to do in our program is check whether the number that strx has returned to us is 1 or not, or is 0 or not. And if it's not 0, that means it's 1. That means it's failed, and our store didn't work. And our only recourse in this situation is to go back and try again. So we're doing a compare R2 into strx fail, and that just means try again here. And if it did return 0, that means it worked. No one's been messing with our memory in the meantime. Then we can continue in the loop, add our 1, and go back to the top of the loop. So this is a good solution actually. This is working completely fine. It's going to solve the problem for us. Someone's asked the question of where this information, this exclusive store, is stored. It's part of the CPU. It's got a special storage location. I guess it's kind of like a register, just some flip-flops somewhere for storing exactly one word of information, one memory address. And on our ARM v7m boards, that's called the local exclusive store. You can read about it in the ARM v7m architecture reference. If you want, I'll talk a bit more about it in detail later, but it's a property of the board. So we have this little place to store this tag, just so we know we've been accessing that bit of memory. This gets us out of trouble. And in some ways, a good way of describing this situation is that this lets us try a load and store, and it tells us if it doesn't work. Because in the meantime, the reason it might not work is that in the meantime, this thread over here may have tried to load this location and stored it, and then hopefully sometime in between, the exclusive store would actually be cleared out. Someone's asked me if there's anything stopping something else from messing with the memory in this case, though. Well, of course you can mess with the count variable, but you can use regular loads and stores. There's no problem. Regular loads and stores will work. There's nothing stopping you doing that. Again, it's up to you as the programmer not to mess this up. If you know that there's multiple things happening, you have to make sure that in these critical sections, you're using sufficient protections to make sure that nothing is going wrong. So one thing to consider is why, if this one is loading R4 into the exclusive store and this one's also loading R4 into the exclusive store, how does this directs know that R4 should be untouched? Riddle me that, Batman. How do we know that R4 is untouched? Because both of them will be wanting to put that memory address count into our store. So our store might be up here. Count. And the reason what happens if someone's asked me what happens if something is tagged as exclusive and another program tries to access, read it? Fine. In fact, what I'm probably about to say will answer this question. When you do a context switch, in fact, when you do any interrupt, the local store is deleted. So if you interrupted, context switch, all bets are off, we clear the exclusive store, and your storex will definitely fail. So the hope here is that we can get this bit done fast enough, this critical section with the letter X storex, fast enough that it's really unlikely to be interrupted. We have no particular guarantee that it won't be, but the only situation in which it can complete correctly is if it's not interrupted by a context switch, because we know that the context switch is going to clear our memory reservation. And actually that's a pretty good bet, because even in a multitasking operating system, it's definitely not like interleaving just every single instruction, right? You'll get a lot of instructions at a go, and then the other process will get a lot of instructions. So it's certainly not going to be always failing, but we certainly want to keep this kind of, if we're doing it this way, we want to keep this kind of exclusive area pretty tight. Wow, a few great questions here, so I might just linger here and see if there's any others, but I don't think so. I'm just going to look in my So Uwe calls this a ask for forgiveness method, right? So this one loads up and tries to store. In the meantime, we context switch to the second one. It loads, does the subtraction, and then does the store, all in that amount of time. The other one goes back, and it finds that everything has gone wrong, and it has to try it again. So this one is just going to jump in, do whatever it wants, and ask for forgiveness later. And going back to the milk analogy, right? I'm imagining, right, person one walks out the door, they go to a shop, maybe they have to go to Costco to get milk, so they've gone rather far away. In the meantime, person two, housemate two, comes home, sees there's no milk, goes to the corner store, comes back with some milk, puts in the fridge. Person one comes back from Costco, really tired, opens the fridge door, and then sees there's milk there, and they just throw it on the ground. There's milk everywhere, right? They're going to be upset with housemate one. Anyway, I've gone a bit mad on the analogies here. Let's move on. Can we approve on this? Well, we've got our critical section, and our critical section at the moment was small, so it was a good bet to do this kind of literex, durex stuff in it. But it might be that we need to do some complex work, and we'd like to lock out some access to a shared resource for a significant amount of time. So in this case, it would be better if we had something up here where we did some negotiations for who gets to go first. So this might be like organizing an asking permission way. This is more like the lock on the fridge. You can't open the fridge until literally the first person comes home and gives you access to the fridge. So this is the negotiating who goes first, and then at the end, we indicate that we've had our turn, we take the lock off the fridge and let the other person go. So let's see how we might implement that. This is going to be using a lock variable. Just like I said, a lock on the door, we're going to have a variable for the lock. So the first thing we're going to do is we've got our count now, and we've got our lock variable there, which at the moment is 0 for unlocked. And in each of our programs, we're going to load up the address of the lock variable, load up the address of count, put 1 into the counter for our for loop, start our for loop, and then we're going to do the negotiation for the locking variable. Here's the negotiation bit. So this is load the lock. Then we check what we've loaded. We put the lock variable in the exclusive store, or the lock variable's address. Check what we had just loaded, see if it's locked. And if it's not 0, then we branch back to here. So the lock variable has to be 0 to be unlocked. 0 is unlocked and 1 is locked. I'm getting some really exciting conversation going on in the chat. I really want to look over there, but I want to just get through this section. So if it's locked, we go back there and just keep checking over and over and over again. And it doesn't matter about we're not checking our reservations after that. We're not trying to store back. We just want to see if whatever is in the lock variable is 0. If it is 0, then we load up 1 into R0, attempt to do our store back into the lock variable, storing it back into there. And we're using storex, so now we can see if it worked or not. Because it could be that just in that little amount of time, just in those 3 instructions, we were unlucky enough for someone else to grab our lock variable, put a 1 in there, and go about their business. So we may have been pipped at the post by someone else racing in and beating us to it. But if we are lucky enough that we manage to grab the lock variable, then storex will have returned 0. And then there's one extra step which Uwe has put in here. It's not strictly speaking necessary on our disco boards right now, but this idea of another instruction which is called a memory barrier, DMB. And that just means that all of the memory operations on the CPU, which might have been queued up, have to be completed before we continue. And that's of more relevance in more complicated systems, but just sort of here for completeness. Okay, so now we've been successful. We've grabbed our lock. Now we've got control of the lock. We've set that value to be 1. We can do our work in the critical section. And now we don't have to worry about literex and storex anymore, because we know we've got the lock and we did enough checking to make sure we were the only one who had it. Critical section goes on, we add 1 to R2, no big problem. And then we're going to get rid of our lock. So Uwe chucked in another DMB there. Just to be safe, we're going to sync up everything in memory. And we're going to do an unlock procedure. And of course, in this case, we know that we're the only one with the lock right now. So we don't need to worry about other people changing. Well, we don't care actually what's in the lock value right now. We're just going to put 0 in it with a regular old store and not worry. And then we proceed with the rest of the loop. So this is our lock variable. And this is a basic implementation in assembly of a mutual exclusion or mutex. Mutual exclusion. And remember, if we're in any of these sections inside this bit that we're actually doing checks on our memory, if a context switch occurs, then all bets are off. The exclusive store location is cleared out and it starts again. So when we come back, that exclusive store will be entry and we know the StirX instruction knows it has to fail. Now there are some problems with this because I suppose, right, if someone had the lock and then they ran a really long program that was really long, just like in the fridge example, someone locked the fridge, then went off to visit their partner. The second housemate would never be able to get into the fridge. And in this situation, we call that a deadlock. So this person, or it's actually called starvation, this person starved because they can't, not deadlock, starvation, because they can't get into the lock. This person's gone off and doing something really long. Someone was asking about that in the chat. You're advised to make sure your critical sections are expedient so they don't hog the lock. So what alternatives might there be out in the big wide world? StirX and LitterX are the way it happens on our ARM processors. But it's not always that way, and we're going to talk about a few other options that there could be. We already talked about the fact that we need some hardware support in order to do this task. We need some kind of way of being sure that when we access memory, we're the only person who's gotten in there. And StirX and LitterX is actually an interesting one because it uses 2 instructions. There's other ways which just use 1 instruction. So I'm just going to talk in brief about this one term, the last term we define here, atomic operations. An atomic operation is indivisible, just like the atom, until we decided to understand how to break the atom and that there's all kinds of stuff inside. So an atomic operation is one that either happens completely or not at all. In fact, this is a word that we hear about in other contexts, in databases, right? You want to make sure you're the only one touching a database. And there's lots of operations we need in the world to be atomic. Bank transfers is a very important one, right? If you send $1,000 from your bank account to someone else's bank account, you want to be really sure that that doesn't get interrupted and happens halfway, because then either one of 2 situations could happen. Both bank accounts could have $1,000, in which case the bank would be unhappy, you and your friend would potentially be happy, or neither bank account has $1,000, they've both got $0, and now you and your friend are unhappy and the bank is like, So atomic operations. This is just a definition of what the word atomic means in this context. So our first alternative is something called atomic test and set. And it's going to be one single special instruction to read a value and at the same time set a value in memory, set it as something atomically. So it's going to be like litter and stir at the same time. So we've got this little pseudocode that Uwe has set up for us to have a look at. We got something called C, which is going to be our little lock, or flag, it's going to be a Boolean value. And C is going to be our version of it, or L is our version and C is the version that's common on the computer. Sorry, that's right. And this is our test and set operation. Uh-oh. Here's the test and set. In the same instruction, we are going to save the value that's globally in the system, save C's value into L, and we're going to set C is 1. And the reason it's atomic is that both of these things are going to happen before, or they're uninterruptible. No other process can get in between those two things and do something else with the global value C. Okay? This is an old school way of doing this. It's been around for a long time. Atomic test and set is used in some processes, not in our disco boards. Not in the disco boards. Jackson's just asked, are we using the definition of atomicity that something is linearizable? I'm not using that definition. I'm using the definition that I gave on the previous page. So it's a instruction where you can't put other instructions in between it. There's other more sort of high-level versions of this concept that are more abstract, apply to other situations. You can worry about those when you come to them. For now, we're just talking about reading and writing from memory. So the way this one's going to work, this is the same mutex. We're just going to keep reading the lock. Every time we read it, we set it to 1. And if the lock is 1 to start with, that means it's locked, and we're setting it back to 1, so no harm done. If we find it's open, we see a 0 there, we set it to 1. So in that instance, we've got the lock, and then we can move into our critical section. Okay, so the same idea, the same mutex. Another one is atomic exchange. So we're going to take a variable and a second variable and sort of switch them out with our flag in memory. So in this case, we're going to do a define temp, a local variable temp equal to L. We're going to define L equal to C, and then we're going to define C is equal to temp. So C and L are going to exchange their values. L is our local version of the flag. C is the one on the global memory. And the same thing is going to happen, right? We'll wait until we find that what we've taken from memory is a 0, and every time we're doing this, we're putting a 1 into memory. Same idea. And now we're just going to go over in the same concept, our way of doing it on ARM, called memory cell reservation, Sturex and Literex. It's also called load link store conditional, I guess in those other 86 processor zones. There's other ways of calling this concept. But we've got this idea that we have two separate instructions. One is going to load our value from memory, and at that point say, that's my memory, put a little sticker on it. And then later on when we try to store to it, we're going to make sure that we don't store to it unless our sticker is still there. And if we see that someone's moved our sticker, we abandon it. So this one is cool because it's interesting because it's got two separate processes. The load part and the store part are separate. The other ones just had one instruction. And this one is what we have. It has some nice features. It gives us this way of doing lock-free mutexes. Like in our first example, we didn't need to have a lock variable. We could just have a very small critical section and just handle it within that. But if we do want to have the locking variable, we can do that too. Now, the thing to remember, the big idea, main big idea from this lecture is concurrency is not an edge case. This is needed all the time, all the time. Whenever you're using your computer, there's loads of concurrency going on. There's processes all the way out the wazoo, right? Look at all the processes I've got. Tasks 384 total, 3 running, 381 sleeping. So I'm sure your computer has many processes as well. So dealing with concurrency is absolutely normal for any programming which will be running on a big computer where people are using it. If you're writing software for users, application software, you'll be dealing with concurrency if you have to interact with a user interface, because the user interface will have its own thread. All of the display stuff will happen in a way where the operating system won't want to interrupt it. It wants to make it all fast and snappy, so we can't put in any heavy processing in that thread. You have to do all your processing somewhere else and then come back to it later. The important lesson you've learned today is that multitask and multi-CPU systems require hardware support to do concurrency. Okay, you need these special operations that give you access to special storage locations. Now you know about how to do LitterX and StirX. You could support synchronization implementations in your code if necessary. I guess the most practical application of what's happened today is that you have the tools required to go and do labs in week 11 and 12. So this is not exactly required for your assignments. This is part of the course to know about this stuff, but it's worked on more in those labs 11 and 12, where you actually get to design a very small multitasking operating system to run two things at the same time, which is a bit of a challenge and a lot of fun, really. Now there's another topic which Uwe, the master of this topic, goes through. Somehow speeds through all of these topics in asynchronicity and synchronization. I'll talk about it a little bit. It's a bit of extra, really. The concept is semaphores. So looking historically, people were thinking about this idea of how to handle computer programs, multiple programs that need to access a shared resource. It didn't always happen on personal computers. It wasn't such a big deal in the 80s, right? Because they were basically single tasking operating systems. But even in the 50s on mainframes, there'd be like one printer, and then the mainframe would be having multiple programs running at the same time, but only one can talk to the printer at a time. So this was obviously an interesting topic. Some clever people were thinking about it, and one of the cleverest was Dijkstra, the famous computer scientist, who defined this idea of a semaphore in the 60s. And it's a generalization of our lock to handle more commonly shared resources, more generally shared resources. And the big difference is that whereas a lock could either be 0 or 1, then the semaphore can be a higher number. So it may be that there's some resource where, you know, multiple programs can use it at once. We can maybe have 5 printers and multiple programs can print to each of those, and our computer needs to handle the case that someone has to come in and someone has to go out. So we can define a semaphore variable S, and we'll have 2 operations for it. And the first is sort of the locking operation, which is called wait. We'll wait and see if S is greater than 0. And if it's 0, that means there's no access left, it's locked. If S is greater than 0, then we're going to decrement S by 1 and then move on into our work with the shared resource. And it's the same operation, right? You'll be spinning and waiting until you see that S is 0, then you go like, until you see that S is not 0, it's 1 or more than 1. Then you go, oh, I can grab a ticket to go and do something, do what I need to do with the printer, and then go back. And then at the end of your critical section, when you've used the shared resource, you can increment S back again, and then you might, if you were nice, you might look over at the queue of people waiting and say, I'm done, someone else go in, right? So this is like when you're at the supermarket at the self-checkout and there's the person there, the employee there who's sort of waving at people to say, oh, you can use this checkout now, right? There's a checkout free, go and jump in there, just to keep the queue moving. So one could definitely, someone's said this is like a queue. A queue is one way of representing this in higher level programming languages or multi-processing queues. S could be 1 or 0, or it could be a higher number. And if it's 1 or 0, just a binary semaphore, that's just like our lock, mutex lock that we had before. Not too hard to write this up in assembly programming. All we have to do is have our semaphore variable here, which is going to start at its highest number. And then in our waiting area, we're going to see if it's if it's 0 and keep loading it in, waiting and waiting and waiting until we find that it's not 0. And if we find that it's not 0, then we can do the decrementing operation. Then we can try to update it. If in the meantime someone pushed it in the line and jumped in before us, we'll have to start the waiting again. But if that doesn't happen, we can go into our critical section, doing our checking out at the supermarket. We walk out of the supermarket, and while we're doing so, we load the semaphore again and increment it, putting out noting that we're not using the shared resource anymore. Then try to update it. And it might be that while we were in there incrementing the semaphore, someone else jumped in and they gave their ticket back as well. So if that happened, we're going to have to go and try the signal process again. In many cases it wouldn't happen, but it might. So it was different than the mutex, the simple lock, because when we had a lock, we knew we were the only one with the key, the only one with the lock on that resource. With semaphores, there might be 5 people or 10 threads with locks on the resource. So we can't be sure when we're putting it back that someone else won't get in there and touch that memory before us. Can anything go wrong with semaphores? Let's just have a high-level view of it. This looks like it should be good. We've got a semaphore that starts as 1. One person can use it at the same time. We do the wait operation. Then we run our critical section. And then at the end of it, we do a signal. There's someone else here doing wait, critical section, signal. And this is probably good, right? So there's not going to be any issues with negotiating the waiting or negotiating the signaling. I guess the only thing that could go wrong here is that someone's critical section could, as we said, be really, really long, and they could cause this guy to starve, right? The skull and crossbones. So, all good. Potentially one progress could starve if the other never signals. We might forget to signal, then we've got a big problem. We could be in strife though if someone had designed the system like this and they had maybe multiple semaphores, maybe there were 2 shared resources that had to be used at the same time, and this programmer, person 1 was responsible for writing up access to this thread. They said wait S1, wait S2, then signal S2, signal S1. That should be good. But programmer number 2 had done it differently, and they did wait S2 and then wait S1. Now what's going to happen if we run this code? What's going to happen if we run this code? We might get into strife, right? Because process 1 is going to grab S1, process 2 is going to grab S2. Now process 2 wants S2, but it can't have it because process 2 has got it. Process 2 wants S1, it can't have it because process 1 has it. And we're not making any progress. So this is called a deadlock. We've both tried to access these resources at the same time, and we're both in this kind of stuck wrestling position where no one can move and we're locked into that position. So in that case, it's complete failure. There's no way out. So we do want to not have deadlocks. And luckily, when we're dealing with higher level systems for concurrency, there would be some protections in place to make sure we can't get into this situation. You generally wouldn't, as a applications programmer, be just coding up your own semaphore system. Your programming language would support it with some standard, and we know it's safe. So do we have to use these in everyday programming? You generally don't have to implement this stuff, semaphores or mutex variables in higher level programming languages. You'll have some higher abstractions or safer solutions. You're going to learn a lot more about this in COMP2300 next semester if you're taking that course. Many of you, it's part of your program, so you'll have to. That's a really great course. It's really exciting. You'll see slides that are a lot like this. This was the kind of overview of these topics for everybody, because this is the common course for all computing students. I think there was there was a little point back there that someone made in the chat about why we kind of do all this stuff in the waiting and signaling areas, why we're putting these checks into those areas. Why don't we just do this in the critical section itself? And the point is that if we do this tricky little operation, the tricky checking, in a very small amount of time, we can minimize the chance that actually this one will fail, right? We can minimize that. And we can maximize the chance that it will work and we don't have to spend too much time waiting. So this is kind of giving us a constant program for doing our checks, and then we get to choose how long this one is. We don't know how long that is. Of course, it's probably better if it's shorter so that everyone gets a turn with the critical resource, with the shared resources, but it's up to the programmer how long that is. At least it's not going to deadlock our system. Yeah, so that's a crucial element of why we're doing this kind of complicated process and not the first process I showed you where we just did the loads and stores in our program as we needed to use those variables. It's much better to use the special exclusive load, special exclusive store for dealing with some other variable, which will act as a lock or a semaphore, and not do the exclusive loads on our working variables. Just because if we were doing it on our working variables, we'd always have to be doing exclusive loads and stores. We're much more likely to interrupt them and waste time in our program. So it's much better just to do it in this very small section. I've got a little bit more to talk to you about on your disco board, but we might come back to that on Tuesday. So if there's some questions, you can pop them in the chat right now. I'll just show you that I've got on this, in the slides for this week, a couple of articles and interesting notes to read. If you want to know more about this stuff, particularly the kind of abstracted version of what concurrent programming might be, then there's this little article from Encyclopedia of Algorithms, which I kind of like, about mutexes, concurrent programming musical exclusion, 1965 Dijkstra. So you can check that out. Otherwise, you can have a look at how this might work on different processes in Wikipedia, looking at load, link, and store conditional or atomic load and stores, and see a few of the solutions we have. There's also an article in a sort of more general article for synchronization primitives that you could check out. And other than that, I might not have too much else to talk about. So I'm just going to jump to the outro. I'll catch everybody next week on Tuesday for our lecture on networks, and I might do a little bit of a demo from the end of this lecture. Otherwise, have a great weekend and see you then. Feel free to ask questions in the chat. I'll be around for a few more minutes before we're taking off. I like reading the chat on Twitch after the lecture. The takeaway from this is that computers are a nightmare, and really everyone has just resigned themselves to that fact. That is correct. Computers are a nightmare. Somehow we get along in our everyday operations, although computers can be a nightmare. So the question is it possible to have multiple processes always reading before others can write with StirX and have a deadlock that way? Definitely that's a problem, and that's why you would want to have a very small critical section or a very small section where LitterX and StirX are used. Otherwise, you could have two threads just deadlocking each other. It's not really a deadlock because there'd be always movement. suppose. The advantage of the lock-free zone, lock-free way of doing it with stirx and litterx, is that even if you fail, the worst that can happen is that you go back to the top of your work and do it again. And that means that there's always progress, right? We may be in a kind of a loop of stagnant process, but we're not going to be at a point where we are not getting any work done. So I think it's I'm not quite clear on the classifications for these different kinds of badnesses that could happen, but I feel like intuitively that it's less bad than the situation with the two semaphores where you don't even get to the main bit of code, but your litterx and stirx could potentially at least be in the main bit of code and have to do it again. We'll have to wait for Uwe to explain it to us all in concurrency and distributed systems. So I just have my big picture and ARM v7m version of the story. It could definitely be a move clock, yeah, a move lock. I do try to read the Twitch chat, but I can't really read any chat while we're streaming because they're so I already have to look at the screen and think and speak and make sure I'm on track, and then I can look at exactly one chat every now and then just to see if there's an important question. So I wish I could combine the Teams chat and the stream chat, or chat from Twitch, but at least this way there's no bots in our Teams chat. Okay, see everybody, I'm going to stop the stream there and make sure you have a great weekend. Bye.